Stop treating energy density as the single metric of progress in electric vehicles. In serious battery engineering circles, this is the most easily manipulated and misleading metric of all. Around 90% of battery startups today deliberately blur the line between material-level energy density measured in laboratories and pack-level energy density in a fully engineered commercial vehicle. The technical reality is far more brutal than flashy headlines suggest. It is not difficult to achieve 500 watt-hours per kilogram in a coin cell charged and discharged at an extremely low rate of 1/10 of the cell's nominal capacity per hour under ideal room temperature conditions of 25 degrees Celsius. But once you scale that cell into a pouch or prismatic format, force it to deliver a 3 times its nominal capacity per hour to accelerate a 2-ton vehicle, and demand that it survives 2,000 charge-discharge cycles in -10 degrees Celsius winters and 60 degrees Celsius asphalt heat, that 500 watt-hours per kilogram figure collapses instantly. The real problem facing the energy industry today is not a lack of new chemical inventions. The real bottlenecks are yield rate and scalability. Elon Musk does not hate new technology, nor is he anti-science. He simply understands a core engineering truth that the media routinely ignores. Chemistry is a necessary condition, but manufacturing engineering is the sufficient one. A theoretically perfect solid-state battery becomes economically meaningless if the production line has a scrap rate above 10%. That is not science, it is economic suicide. To understand why we still do not have a super battery, and must confront the enormous gap between the laboratory environment and the factory floor. In the lab, battery development resembles handcrafted jewelry making. Scientists can use ultra-pure materials that cost as much as gemstones handled inside argon-filled glove boxes to eliminate contamination. If they produce 10 cells and one performs perfectly, that is considered a major success worthy of a published paper. Factories do not work that way. Factories demand ruthless uniformity. For a battery to be commercialized, it must reach a cost target below $100 per kilowatt-hour. That means producing millions of cells per day at extreme speed with defect rates measured in parts per thousand, not percentages. Look at the reality of 2025. Billion-dollar startups branded as breakthrough technologies such as QuantumScape and solid power remain trapped in the manufacturing valley of death. Their fatal weakness is scrap rate. When transitioning from manual assembly to roll-to-roll automated production novel material, layers frequently tear, wrinkle, or fail to bond properly, forcing 30 to 40% of output to be discarded. In manufacturing economics, any scrap rate above 5 to 10% means a company is burning cash at an unsustainable pace. Now contrast that with Tesla's approach. Tesla deliberately accepts a slightly lower theoretical energy density with its 4,680 cells compared to the most advanced laboratory concepts. In return, it optimizes mechanical processes to achieve 60 to 100 cells per minute in casing and winding speed. That throughput, combined with ultra-low defect rates, is what actually prints money and drives EV prices down. The real question for the market is simple. Would you choose a perfect battery costing $50,000 or a good enough battery costing $5,000? Solid-state batteries are often portrayed as the holy grail because they replace flammable liquid electrolytes with solid ceramic or polymer materials, promising absolute safety and higher energy density. Behind the curtain, however, lie massive physical and mechanical engineering barriers. The first is lithium dendrites. During fast charging, lithium ions migrate from cathode to anode. At the anode, typically lithium metal in solid-state designs, they tend to deposit unevenly, forming needle-like structures. In liquid batteries, this is already problematic. In solid-state systems, these dendrites are rigid enough to pierce ceramic separators, causing instant short circuits. This is a fundamental physical limitation, not a software bug that can be patched overnight. The second rarely discussed issue is stack pressure, the Achilles heel of solid-state batteries. For ions to move through solid layers, those layers must remain in extremely tight contact. Any microscopic air gap caused by expansion and contraction during cycling kills the cell. As a result, solid-state packs require external clamping forces measured in hundreds of psi, forcing manufacturers to add heavy steel frames and complex compression mechanisms inside the pack. The irony is brutal. Even if the cell becomes lighter, the pack often becomes heavier, erasing most energy density gains. Now consider the promises. Toyota first announced solid-state batteries around 2020, then delayed to 2025, and now speaks of limited production in 2027 to 2028. In reality, this functions largely as a strategy to reassure shareholders while slowing the transition to full battery electric vehicles. NIO's 150 kilowatt-hour semi-solid battery launch delivered a similar reality check. The battery alone costs roughly as much to lease or purchase as a brand-new Tesla Model 3. A technology that has been 5 years away for 15 years raises an uncomfortable question. Is this innovation or a belief-based Ponzi scheme? While academia dreams of exotic materials, Elon Musk and Chinese manufacturers such as TATL and BYD pursue a far harsher path. Supply chains and structural engineering matter more than chemistry. The rise of LFP is the clearest example. Once dismissed as low-end due to lower energy density, LFP offers 3 decisive advantages: no cobalt, exceptional thermal safety, and rock-bottom cost. Musk recognized that for 80% of consumers, 250 to 310 miles range is sufficient if the vehicle is affordable and durable. By 2024 to 2025, LFP surpassed 50% global market share, a clear victory of industrial pragmatism over laboratory idealism. The 4680 tabless revolution follows the same logic. Instead of changing battery chemistry, a high-risk move, Tesla redesigned the physical structure. Traditional cells force electrons to travel long spiral paths to reach current tabs, generating heat through joule losses and limiting charge rates. The tabless design turns the entire edge of the current collector into a conductor, shortening electron travel from meters to centimeters. This is not material science magic, it is pure electrical engineering. The fundamental difference between a materials scientist and an automotive CEO comes down to one word: responsibility. A scientist is accountable for a successful paper under ideal conditions. A CEO is accountable for delivering millions of vehicles that operate in snow deserts, rain without fires, and at a profit. Batteries are not fascinating science experiments meant for admiration. They are industrial commodities like steel or plastic, and must be produced at scale with near absolute reliability. The final warning for anyone following this field is simple. When you see a headline claiming 1-minute charging for 1,000 kilometers range, ignore the glossy specifications and ask a single question. When will their factory ship 1 million units per month?